Hello everyone, and my name is Ching, and today I'm going to talk about improving domain adaptation by using self-supervised depth. Domain adaptation aims to adapt knowledge from a labeled source domain to a similar but different target domain. For semantic segmentation, the domain difference could be between synthetic images and real images, between different weather conditions, etc. In the unsupervised domain adaptation setup, we have access to some RGB training images and their corresponding semantic labels for the source domain. And we additionally have some unlabeled images for the target domain. And our aim is to improve the segmentation performance on the target domain. So in this work, we focus on using depth to improve segmentation performance in domain adaptation. And this is motivated by the fact that depth and semantics are highly correlated. The sky is always far away and rows and sideways are always flat, and these domain-robust correlations between semantics and depth has the potential to largely improve segmentation performance on the domain shift. There are existing works which explore the possibility of using depth to improve domain adaptation. And in these works, it is often assumed that we will get access to very precise depth maps from the source domain, but no depth information from the target domain. However, this assumption largely restricts the applicability of these methods, and in the real world, we know it is very hard to obtain highly precise depth maps, and therefore, ground truth depth maps from the source domain may not be available. In addition, depth information in the target domain is not used at all. But it's actually possible to get rough depth information for the target domain by using a moving camera or stereo cameras. Since precise depth maps are often missing in reality, and this limits the applicability of this method, a natural question comes: how can we still benefit from depth when there is no depth ground truth? To overcome the limitation, we propose to use self-supervised depth estimates as pseudo-ground truth. A recent progress on self-supervised depth estimation makes it possible to get depth estimation from either video sequences or stereo pairs. For example, by using off-the-shelf solutions such as monodepth, pseudo-depth information can be easily generated from a moving camera. And this self-supervised depth estimation process can be applied for both the source domain and the target domain. The additional depth enables us to exploit the correlation between modalities. First, we learn the domain-robust task feature correlation and transfer it to the target. And second, we approximate the adaptation difficulty from depth and transfer it to semantics. We adapt recent developments of multitask learning and use attentions to learn the correlations in the source domain. We then share it to the target domain. We first learn the task-specific features by using initial prediction heads for semantics and depth. We have a shared semantic decoder for both domains and two individual depth decoders. When the task features are ready, we make use of the two attentions to capture the mutual relationship between depth and semantics. This attention captures the complementary information from the other modality and ignores irrelevant information. The learned correlation is then shared across domains. And given the distilled features, we use a shared semantic decoder for both domains to perform the final predictions, and the depth decoders for the two domains remains independent. As depth and semantics are naturally coupled, we transfer the adaptation difficulty of depth and use it to refine the semantic pseudo-labels. Given a target image, we approximate the adaptation difficulty for each pixel by calculating the prediction discrepancy between source and target depth decoders. We make the assumption that pixels that are hard to adapt for depth are also hard to adapt for segmentation, and we use it to reweight the pseudo-labels. Combining the two ways of correlation exploitation leads to our proposed correlation-aware domain adaptation method. We conducted Ablation Study on the standard benchmark Sincere to Cityscape, and results show that both components in our methods are effective, and the final method yields a significant improvement over a strong baseline. We compare our results with state-of-the-art methods, and we include other methods that also uses depth information, and the proposed approach outperforms all the others, and experiments also show that both monocular and stereo depths lead to a similar strong performance. We also evaluate our method on the popular GTA to Cityscape benchmark, and our method again outperforms the other approaches by a margin. To sum up, we show that self-supervised depth and correlation learning can largely improve domain adaptation performance. Our code is online, and I'm looking forward to your questions.